In this video, we're looking at accumulation functions. And I think students sometimes can have a hard time with accumulation functions, even though the idea is pretty easy. So let me try to make a picture before we move on. Let's say we have some function that looks like that. And here's my, for some reason, I just want to start measuring area from 2. So if I'm looking at the integral of my function, just say it's f of, let's say f of t from 2 up to some unknown amount. So we don't know how far we want to start measuring the distance or the area underneath the curve, but we're measuring area underneath the curve. So here's my f of t and t. So clearly, you know, as x goes, if we let x start at, let's just start it at 2 for right now. As x gets bigger and bigger and bigger and bigger, we're integrating from 2 to a larger number. So from, imagine x being, 3 and then 4 and then 5 and then 6. The bigger we let x get, the more area there is. So if we were evaluating it at 5 versus 6, from 5 to 6, we're adding more area. We're accumulating. So the idea is, this is called an accumulation function because depending on, as x grows, the area, the definite integral, will grow as well. So let's suppose that a is a fixed number. Try to write down in a sentence, and I want you to actually do this. Write down in a sentence, what is the function a of x evaluating? Well, hopefully you've paused and tried to do that. What it's finding is the area, just like what we just did, the area under the curve comma f of t, where f of t is the curve, from t equals a, some fixed number, to t equals x, some varying number. All right, let's look at some concrete examples of this. First, though, before we look at a concrete example, I just want to make sure that we're clear on one idea, which is going to be helpful for us as we do accumulation functions. The idea that is, what I'd like you to do is explain, using the fundamental theorem of calculus, why the following is true. So write down on a piece of paper, and I want you to explain why the following is true. And once you've taken a stab at trying to explain it, I will do the same thing. Okay, so let's say little f of t is the derivative of big F of t. Okay, so this then, using the fundamental theorem of calculus, the left-hand side is f of x minus big F of a. And what we're saying is that it equals the negative when we switch the limits of integration. Well, that becomes increasingly more clear when we use the fundamental theorem of calculus. So we have the negative out in front, and then it's big F of a minus f of x. And if we distribute this negative, and rearrange the order, we're left with f of x minus f of a, which is exactly what we had over here. This is going to be a useful skill. We're going to use this idea of putting a negative out and switching the limits when x is less than a, because typically we like to put the smaller number below and the bigger number up top. Okay, so here's an example of an accumulation function. So we know that distance is the integral of our velocity. So what we're saying is that we're integrating our velocity from t equals 0 to t equals some unknown time for some time between 0 and 5. So we're measuring, because 0 is our initial point, we're measuring from t equals 0. So in other words, this is finding the displacement it's finding the displacement of our walker or whatever's moving. It's finding the displacement from t equals 0 to t equals some unknown time. And as time increases, let's think about, right now we're at this big T that we show is 2.5. And if we were to put this 2.5 in, our displacement would be 1/2, 1.5, 2, 2 and a little bit. So this area would be like, let's say 2.1. But as T goes on, we're accumulating area. It may seem like a simple idea, and it really is. So if it feels that way, let it be that way. Okay, in this text problem, we're not starting from 0. We're starting from -3. So that's we're measuring our accumulation. So we're beginning our measure of accumulation at t equals -3. So this is where we're starting our measurement. So when x equals -3, we'd be when x equals -3, we're integrating from -3 to -3. So there's no base. So our g of x function would be 0. And when we're integrating from -3 to -2, now we're talking about this area, which has an area of 2. And then from -3 to x equaling -1, now it's this entire area here. So that is the 2 from before, plus we've added 1.5. So now we have a total area of 3.5. And if we look at to 0, that adds this little component. So now we're at an area of 4. And an important reminder, when x equals 1, now we're looking at the area, this whole area, which was 4, plus this area here, and that area there, because it's below the x-axis, is negative area. So that's going to take away from my function. So just because it's called accumulation doesn't mean it always grows. It could also shrink. So now we're back at 3.5. And then from when x equals 2, we're taking away more. So now we're at 3. And when x equals 3, now we're starting to add area again. So we're back at 3.5. So to sketch a graph of g, we just plot all these points. So when x equals -3, g equals 0. I'm going to need a good marker to make this clear. And when x equals -2, we're at 2. -1, 3.5. 0, 4. 1, 3.5. Oops, that's right there. 2's at 3. And 3's at 3.5. So it's going to look something like that's what my g function looks like. And it's looking at the growth. It's looking at how it's looking at the growth of my function. So it's looking at the accumulation of area under the curve as x starts at negative, from starting at -3 and going onwards. So which is larger, g of 0 or g of -1? Clearly, g of 0 is bigger because between 0 and 1, I'm losing. I've got a negative area, so I'm losing value. And where is g increasing? Well, g is increasing everywhere where my little g of t function was above the x-axis. So it's increasing from -3 to 0 and from 2 to 3. Okay, so I think this is the last example that we're looking at. It's a sketch a graph of this function. So let's do that first. It's a linear function. So here we have f of t and t. We start at 6. We go down at a slope of -2. So this then would be the point 3. And it says with f defined by f of x equals the definite integral from 0, so starting our measurement at 0, to x of this function that I just drew, little f of t, evaluate the following: f of 0, f of 1, and f of 3, using the area formula for a trapezoid. Well, I'm not going to do it using the area formula for a trapezoid. We know that the area of a trapezoid is 1/2 height 1 plus height 2 times the length. Instead, what I'd like to do is think about generating an equation for f of x and then plugging in these points. So if we integrate 6 minus 2t dt from 0 to x, what I'm going to get, if I look at the right-hand side, the integral of 6 is 6t, and the integral of minus 2t is minus 2t squared, and then divide by 2. And I'm integrating that from 0 to x. So using the fundamental theorem of calculus, well, that is the fundamental theorem of calculus, and now we're gonna plug in x and we're gonna plug in 0. So we get that this equals 6x. Well, the 2's are going to cancel out. So minus x squared. So we plugged in the top limit, and now we plug in the bottom limit. But when I plug in the bottom limit, I'm just going to get 0. I'm just going to get 0. So this now, this is my expression for big f of x. Big f of x equals 6x minus x squared. So if I want to find, if I wanted to find f of 0, plugging 0 and you just get 0 back. And that makes sense because f of 0 would be integrating from 0 to 0. And if you integrate from 0 to 0, there's no width, so your area would be 0. F of 1 would be 6 times 1 minus 1 squared, which is 5. So that's like this area here. And then F of 3, plugging 3 in, we get 9 back. And it makes sense that F of 3 is bigger than F of 1 because we continue to accumulate positive values. So that's that. What I do want to do though is make the difference just to make it really clear. What we were doing here is we were measuring the accumulation from starting from x equals 0. What if doing a very similar problem? What if on the next page we said that f of t once again is 6 minus 2t, and instead of starting at 0, we integrated from 1 to x. We said big F of x is the integral from 1 to x of little f of t dt. Well, the difference here, the difference is that because we're starting at 1, if I were to find, if I wanted to find f of 3, because I'm starting at 1 already, f of 3 in this case is going to be smaller because I'm not including this area right here. And I'm not including it because my starting point is 1 as opposed to 0. And let's just go through the mechanics to see what this function would look like. So this is the integral from 1 to x of 6 minus 2t dt. We take the antiderivative. So we get 6t minus 2 over 2 t squared, same as before. And now my limits of integration, instead of being from 0 to x, are 1 to x. And this is where the key difference is going to occur. So when I plug in values, I'm going to get 6x minus x squared. Now I'm going to be subtracting minus 6 minus 1. When I plug 1 into this, I just get 1 back. So my function, my accumulation function, ends up being 6x minus x squared minus 5. And what is that minus 5 doing? Well, this minus 5 is subtracting the amount that we would have accumulated from 0 to 1. And we're subtracting that minus 5 because we only are concerned with measuring from 1 onwards. So that's a subtle but hugely important difference for us to recognize between accumulation functions. The one that we looked at first, we were measuring from 0. That we were starting our measurement from 0 here, versus this other example where we were measuring from 1. And the idea being, or the key difference being, is that f of 3 in our scenario here if I were to plug 3 into this function, f of 3 is 4. This area ends up just being 4 here, whereas in the previous example it had been 9. And the reason why it's less, the reason why it's only 4 here, is because we didn't include all of this area right in there, because we only started our measurement. We started accumulating from 1. That's our starting point.